Yes.
Yeah, is the review, there's like a review on Canvas for exam one. Is that accurate for this year's exam one?
Okay, so the question was, is Canvas accurate? And I don't know. I didn't. How about if I poll the TAs and the professors, make sure. I know we've assigned an exam one review sessions, like we did lab lectures, like we did introduction to C. We will have it. Whether it's accurate or not, since I didn't post it, I don't. Most likely because Canvas doesn't. Piazza could have stuff from Piazza can have stuff from last year, but yeah. Okay, can we just say I don't know?
Yeah.
I'll check it.
Our first test is 2 weeks from this Friday.
Okay, it's not today, I hope.
Yeah.
Okay. Yes. I mean, the syllabus is absolutely correct. About the question is, when are the exams? The exam one and exam two are properly listed in the syllabus. The final is still in negotiation. Hopefully we've requested a commons final, but at the date, I don't know. Did that answer your question? Yeah. Okay. Like I said, I'm going to tape this for those who went to the career fair. My goal for today, as always, is talk a little bit how 312H fits into 319K. In particular, we're going to show you malloc and free in that array example you did in class with much smaller stuff. We're going to finish up our discussion of, Lab 3, which includes hardware interfacing, timing, this whole essence of duty cycle, which we call pulse width modulation, and again, questions? Okay, yeah.
So in this, I guess, lab that we're doing right now, we're interacting with two pieces of hardware. One is the actual blinking LED, and the other is the actual oscilloscope. Because the oscilloscope should send data about like the timing, right? That's
okay.
How we
so the question is, yeah, there's hardware in Lab 3. One of the hardwares is, assuming this still works, I will pass it around, and I want to use it later. But the hardware for Lab 3 is the light will flash. Okay, the light is still flashing. Okay, and as you push the button, the duty cycle of the light will change. Okay, and we'll talk about breathing later. But we're going to need to. This is hardware. Don't take a picture of this because my switch is different than your switch. But then the other piece of hardware is the oscilloscope, which we use to measure timing, and we're going to do that again today. So I'm going to pass this around, and yeah, if a wire falls out, it's broken. I'm sorry. I'll put the wires back in. All right. Okay, so let's do. Let's review or show you how malloc and free would instantiate itself on in 319K. I need a internet. Okay. How did Dr. Guglart show you blinky? Okay.
Hey, Binky, wake up.
Okay.
It's time for
noise here. Hey,
pointer fun.
Blinky, hold on, he's not making any noise. Hold on.
Learn about pointers. Oh, goody.
Blinky.
Well, to get started, I guess we're going to need a couple pointers.
Right,
Okay, this code allocates 2 pointers which can point to integers.
This way.
Okay, well, I see the 2 pointers, but they don't seem to be pointing to anything. That's right. Initially, pointers don't point to anything. The things they point to are called pointees, and setting them up's a separate step. Oh, right. I knew that. The pointees are separate. So, how do you allocate a pointee? Okay, well, this code allocates a new integer pointee.
Okay, my trouble is my...
All
right, I'll start it over.
Hey, that looks better. So make it do something.
All right.
Hey, Binky, wake up. It's time for pointer fun.
All right,
What's
so
that? Learn about pointers? Oh, goody! Well, to get started, I guess we're going to need a couple pointers. Okay, this code allocates 2 pointers which can point to integers. Okay, well, I see the 2 pointers, but they don't seem to be pointing to anything. That's right. Initially, pointers don't point to anything. The things they point to are called pointees, and setting them up's a separate step. Oh, right. I knew that. The pointees are separate. So, how do you allocate a pointee? Okay, well, this code allocates a new integer pointee, and this part sets x to point to it. Hey, that looks better. So make it do something. Okay, I'll dereference the pointer x to store the number 42 into its pointee. For this trick, I'll need my magic wand of dereferencing. Your magic wand of dereferencing? That's great.
All right, this is the code.
This is what the code looks like. I'll just set up the number and... Hey, look, there it goes. So doing a dereference on x follows the arrow to access its pointee, in this case to store 42 in there. Hey, try using it to store the number 13 through the other pointer, y.
Oh, wait for it. Wait for it.
I'll just go over here to y and get the number 13 set up, and then take the wand of dereferencing and just... Whoa! Oh, hey, that didn't work.
Binky explodes.
Say, Binky, I don't think dereferencing y is a good idea, because, setting up the pointee is a separate step, and I don't think we ever did it. Good point. Yeah,
so
we allocated the pointer y, but we never set it to point to a pointee.
Write into ROM.
Very observant. Hey, you're looking good there, Binky. Can you fix it so that y points to the same pointee as x? Sure, I'll use my magic wand of pointer assignment.
So again,
is that going to be a problem like before?
No,
this doesn't touch the pointees. It just changes one pointer to point to the same thing as another. Oh, I see. Now y points to the same place as x. So wait, now y is fixed. It has a pointee. So you can try the wand of dereferencing again to send the 13 over. Okay, here goes. Hey, look at that. Now dereferencing works on y. And because the pointers are sharing that one pointee, they both see the 13. Yeah, sharing, whatever. So, are we going to switch places now? Oh, look, we're out of time. But just remember the 3 pointer rules. Number 1, the basic structure is that you have a pointer, and it points over to a pointee. But the pointer and pointee are separate, and the common error is to set up a pointer, but to forget to give it a pointee. Number 2, pointer dereferencing starts at the pointer and follows its arrow over to access its...
All right, so the point is, you have a pointer, you gotta set it to something before you write to it. This is my simplified introduction to malloc. Malloc is something you can run in C. You give it how many bytes you want, and if you're too lazy to know that 16 bits is 2 bytes, you can go size of. In this case here will return a 2. Size of right here, this will return a 2. This will be 20 bytes. Malloc returns what's called a void pointer, and so I'm going to typecast that pointer to a character pointer, and now yeah. So
20 bytes?
Yeah, why? Why isn't that not an end pointer?
Isn't it 200 bytes?
200 bytes. Sorry, did I say? I don't know what I said. It is 200 bytes.
What's the void pointer?
Yeah, that's the return value of this, and so that's actually type. Let's fix that. Let's fix this. This should have been a. This should have been a.
No, he's cast because.
I'm casting it so P is of type int 16-bit integer, right? P is a pointer to an array. Okay, P is a pointer to an array of 100 bytes. Okay.
What can and can't you cast?
You can cast anything, but you want to cast things carefully is the answer to the... He said, what can you cast and what can you not cast? Yeah, it's a tricky thing. The malloc is going to return a pointer of a type that's not known. It's called a void pointer, and so I'm going to change the pointer type to 16-bit integer pointer. And so then once you have a pointer, you can use the pointer however you want, because if you have an array, if you just use P, you get the address of the first element. If you index on a pointer, right here, you get a pointer. You dereference that pointer, allowing you to store into it. So, what is the difference between this line and that line of I? equals.
Parentheses?
Do I? Who knows? Yeah. No, that's just PowerPoint telling me it's an error. Yeah. All right. Those two are the same thing. Okay. P plus n is actually P plus 2 times n. And then you allocate it. You allocate it. You use it, and then you kill it. Okay. Let's. So the idea of Blinky was make sure you create the space and set the pointer before you access the pointer. That's the point of Blinky. Okay. Now courses later on will teach you how to write malloc and free. Both the Ramesh's operating system and Guschlauer's operating system class will show you how to write malloc and free. At this point, we're just going to use it. Okay. This is very close to the example that you did in class this week in 312. I did one thing, I think, I did a couple of things. I added the output init so that actually printf would work, and I changed the size of the array to much smaller. Okay, so I am going to run this code on the board. Well, I guess I'll run it on the simulator. I'll run it on the simulator, and I want to focus in on this line right there, because let me flip over to the board, to the debugger. Okay, where are we here? And that's not this one, that's the other one. Okay, save, sure. All right, so if you were to look at this line of code, let's break it into its parts. What is that? What is it? What number is it?
32.
No.
Depends.
No, well, okay. It depends in life, but in this compiler, it is a 4. Okay? Number of rows in this particular example is going to be called with rows 10. Okay? This is going to be called with a 10. And so this is going to give me 40 bytes of stuff. Okay? I'm going to get 40 bytes of stuff out of here. Now, Milos didn't typecast it. Because it's a void pointer, you can write it to anything. Okay? But suffice it to say, malloc gives you a pointer, and that pointer has no type. It's a pointer, but it has no type. But once I store it into matrix, it now has a type. Okay? And so I would like to run to this spot and demonstrate to you what type it is. Okay? You with me? Okay. All right, I'm going to ask you what type it is, but you may or may not know. We'll ask, what type is it? Something special about the... Okay, when you have a single star, what does it create? Pointer. When you have 2 stars, pointer to a pointer. Yeah, because you're smart. Okay, so then maybe I don't need to do this. I'm going to zoom in. I'm going to. You see, I put a breakpoint right there. Oh yeah. Before I get any further, I will tell you, if you're going to practice at home, now 319K will require no malloc and free until we get to lab 8, in which we're in C++, and then we will have a heap. But there's our heap, 1,024 bytes. Okay, and I stole it out of the memory allocation. You had 32,000 kibibytes. I stole 1 kibibyte for heap. Okay, and as you know, we have 1 kibibyte for ROM stack. We did that last time. All right, so that is the 2 changes I made to this program, to Milos's program, to make it run on this device. Okay, so build, debug. All right, run. All right, run. Okay. All right, so I haven't executed it yet. Okay, and so there is the ×4 up there. There's the call to malloc. Interesting. You can tell me what type of variable is matrix. What type of variable is and small matrix? Right here, line 15. What type of variable? Local or global?
Local.
Local. Where is it? Look at the yellow. Look at the yellow line. No, it's not in R0. It's in R7. R0 is what? The return parameter in ARM architecture procedure call standard. Okay, so R7 is matrix. Okay, all right. So I'm going to execute step over because I don't want to go through. I don't want to show you how it works. I want to show you how to use it. So I stepped over, and so now I look in R7. And I see 2000 with a bunch of zeros, 18. I happened to play this game before class and typed in 2018 in my memory window. You remember it is 10 things. And so one of the cool things you can do with the device here is to change the size of this window. All right. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. I got too many. Take away 2. Come on. 1, 2, 3, 4, 5, 6, 7, 8, 9. Oh, one more. All right, don't matter. All right, okay, one more.
One more.
One more. All right. So the first row here is the contents to which matrix is pointing, right? Matrix is in R7. R7 is 2005 zeros 18. And at 18 are 40 bytes of stuff. Okay, what can you tell me about the heap when you get stuff? What's its value?
Random.
You don't know. Okay, fine. So you don't know it. And so just because we got 0 here, we're not going to assume it's always going to be 0. But what happens next? Okay, let me step over. All right, what just happened to the first element of the array pointed to by matrix? It got something. It's no longer 0. What is in matrix? That's another pointer. Okay, so that was you guys jumped on it's a pointer to a pointer. And I'm showing you that R7 is a pointer to here. At here is a pointer to the actual data. Okay, so let's look at the data. Let's look at 48. 48, he said. 48, yeah, 48. Okay, and yeah. 48 is what thing? Okay, in this case here, how many? I had 3 columns. So these 1, 2, 3 represent the 3 pieces of data. Now it hasn't filled it with crap. I have to fill it. So if I step over this 3 times, you will see that it filled a 2, a 7, one more, it filled one more. Right. Okay, now he said, what is it? And I says, whatever you want. Okay. He said, what is the type of that? And the answer is however you want it. Okay, so if you would like it to be decimal, you can click decimal. Okay. If you would like it to be hex, you can get rid of the decimal. Okay. So you can see that this particular thing here is not decimal. Okay. You can also change the size. All right. So you can change the size to be 8 bits, 16 bits, or 32 bits, or 32 bits. I don't know why. Or ASCII or float or double, whatever, however this is. Okay. Let me run to this spot, and it'll be all done at that spot. And we'll be able to see, run right there, run to there. Okay, so I'm going to make a mess of this window now. Let me go back to show you this one before I make a mess. Okay, what are these numbers here? 2048, 58, 68, 78. 88, 98, A8, B8, C8, and D8. Those are pointers, an array of 10 pointers. Okay? And so down here, if I wanted to actually see the array in its beautifulness, okay, I could make it 3 wide. Come on. Okay. And there it is. Okay. There's my matrix. Row 1, row 2, row 3, row 4, column 0, 1, 2, 3. There's my matrix. Filled up with random numbers here. Just to, as you know, if I hit the go button, and I move this guy, I can't call stack. There we go. Let's go here. If I hit the go button, it'll print those numbers out in the screen. All right. So Malik returns a pointer. You assign that pointer to something of type, and then you're good to go. Questions on that example? Yeah. Oh, my favorite command, reset to default. Yeah, reset to default use. Okay, so it goes all back to where it was. All right. Questions on this? Oh, I got another one. I forgot to show you how I wanted to show you some magic. All right. Okay. Right here. All right. So the question is, what is this operator?
Modulus.
Modulus. How does it work?
Remainder.
How does it work? Yeah, there's no opcode for it. So there's the 10 right here. Okay. There's a divide. There's a multiply, and what is this opcode? Yeah, I don't know. Okay, he's guessing. See, none of you failed the course last semester. You don't know what that is. Left shift. Yeah, no, it's not a left shift. So this one was in the book. That one was in the book. So you might go, hey, John, what is it? And let me teach you how to look stuff up. Sure, let's look stuff up. Help. Help. So I'm going to type it right here in the search window. And then I'm going to hopefully, what? Like, there's only 5 choices. I click on the first one and I go, that don't mean anything. So it helped. So let's click on the second one. It's not like Google, where the first one is always right. Okay, there we go. Multiply and subtract. How many parameters does it take? How many parameters does it take? 4. What addressing mode is it? Register. They're all registers. Okay. So, yeah, that's how the divide is implemented. Okay. Take a note. Lab 7, you need to implement modulus in assembly. Okay. So I'm just warning you. It'll come up in lab 7. All right. And, this is one of the things that there's also a modulus in the book, and you might imagine my assembly code is not as good as the compiler code. I had a great sadness this morning when I looked that up, and I go, oh, I've been doing it so slow. But nevertheless, questions on this? Oh, yeah, one last thing about matrices is what if you're taking 319K? You just might happen to be taking, you're taking 319H. But the other way that we will see matrices in 319H is static allocation. This was dynamic allocation. If you had a 10-row, 3-column device matrix, you could put it in global RAM like that and access it like that. And as you know, that line and this line are identical. Okay? So you access the statically allocated array just like the permanent, like the dynamic array and static allocation arrays are accessed the same way. So but obviously Milos's code is better than this code because it allows you to dynamically create it at whatever size you want, use it, and then destroy it, right? You can destroy the matrix when you're done. A static allocation exists forever. Interesting sidebar, which one's faster?
No, not the right.
They're both the same speed. Okay, because yeah, you think this is fun because you got a compiler, man. The compiler's like totally awesome. Look at how it accessed. That is the dynamically allocated array, right? Look at what it took to actually access the array. How many opcodes? 2, 4 bus cycles. Yeah, because you can put registers inside of, so this particular addressing mode right here is R4 times 4 plus R7. This one is R8 times 4 plus R0. Okay? So anyway, it's because this first one here is, because it's a star, right? The first one here is dereferencing the first address, and this, you notice how R1 maps from here to there? Okay, R1 is the first address, and it's dereferenced in the second operand. Really fast. Because the folks at ARM knew you wanted to use arrays, so they made addressing modes so that it would be fast. Okay? All right. All right, enough of that. Okay, so I'll say it again. Any questions on this? All right. So in a summary, we've actually seen all 4 types of variables so far. Okay, 4 classifications. We started out with locals. Locals were divided inside the function. They're temporarily allocated in registers if we can, and privately scoped to that brace. And then we also talked about globals. Globals are permanently allocated and everybody can access it. If you add a static to a variable, whether that variable is inside the function or outside the function, what it does is make it permanently allocated but restricted scope. And now we have the opportunity to have public temporary variables. Okay? So if you go back and look at this code right here, that's not that one. No, let's go back one. Okay, that one. Okay, if you go back and look at this code, what is P? Is it P? Is it global, local, static?
Global.
It's global. Okay? P is global. What P points to is temporarily allocated. Okay? So this is if you want to have a global, temporarily allocated, parameter, you make a global pointer, and then you malloc and free it. Okay? If I were to add static in front of here, what would happen? Now, how is it different? It's still allocated in the heap dynamically, but what is its scope? Private to what? Yes, it does matter. Private to what? To the file. Okay? What if I did this? Okay. Don't write this down. This is really bad code. First of all, it won't compile, but I did something horrible here. What did I do? I allocated space, put it into a local variable, and then when I returned, what happened? I leaked it. It's gone. I got no more pointer to it. I can't deallocate this anymore. I can't, since it's not shared here, I can't deallocate this. So this is a bug. This is a serious bug or stupid. This won't even compile. Won't even compile. All right. All right, okay, so let's talk about 319. Any questions on your 312 stuff that relates to 319? All right, so as a summary from last time, the behavior of this is this is an input to the pin. Okay, the B is an input to the pin. What do I connect it to? What do I put right here? Yeah, I put it to to an output port. I connect B to an output port right here. Okay. What is E? That's the ground. We're going to ground it. And C is the output of the chip, which goes to my circuit. What is the behavior of B to C? If B is high, what is C? Low. If B is low, what is C? No. Well, half of you are right. Float. Okay. Low goes to float. Okay, which means no current, no voltage. All right. So how we used it was like this. What it actually is, I think when I did this on Tuesday, I might have written 0.5. You're going to measure what it is. Okay. So when the output is high, when the port pin is high, the B is high, the C is low, some voltage near 0, and then we're just going to do Ohm's law on the. I'm just going to do Ohm's law on the series combination of the resistor, the LED, and the ground. Okay. Realizing that V times I is the power, which will determine the brightness. So what we're going to do now today is flash it fast enough so you can't see it. That's my plan for today. All right. Questions so far? That was a review. All right. So what I've done is rather than do this one, what I've done is, okay, where aren't you go here? All right. Is I copy pasted from the first week. I copy pasted from the first week the following code. Okay, so if you remember this operation, it flashes port F bit 0. So let me actually build it, download it. Okay, so it flashed port F bit 0. Okay, we saw on Tuesday 3 different ways to measure the rate in which it flashes. What were those 3 different ways?
Logic analyzer.
I could use the logic analyzer in the simulator. Okay, so I could go over to the simulator. Build. Okay, well, with full disclosure, I added these 2 lines of code, which actually makes it run now at 80 megahertz and invokes the oscilloscope onto Texas display. So everything but those 2 lines of code were the thing we did the first week of the semester. Okay, build. So I could add a logic analyzer. This happens to be port F bit 3. And we want a bit. Close, run. All right, stop, zoom out. No, zoom in. That'll work. Stop. That'll work. Stop. Okay. So I could show the cursor, click right here, move over there, and I see that it takes 50 milliseconds for the delay loop to happen. Okay. Okay, you see that? That was the one way with the logic analyzer. I'm running in the simulator using the logic analyzer. What was the second way? Calculated, yeah, I just do it the hard way. Yeah. Yeah, so we can, turns out this
it's
thing.
One way, I mean.
Yeah, it's a way. It's not a good way, but it works in this particular case because I can turn on the show time right here, put a breakpoint there. First time through the loop, I can see that it took it took, this number here is 1,000,000. This instruction was executed 1,000,000 times, each one being 12.5 nanoseconds, so that was 12.5 milliseconds to execute this instruction 1,000,000 times. This one took 3 bus cycles, and so 3 times 1,000,000 times 12.5, and there's my this plus that is 50. Okay? That's okay. Both of which are wrong, by the way. Okay? Because the assumption here was that this instruction took 1 to execute, and this instruction took 3, and the assumption was it was permeated by the simulator, which also thought that, but it doesn't, because life is way more complicated than simulation. So in order to do it better, we're going to stop the debugger, download it to the code. I actually already downloaded it to code. I have a special power here in lab 3. PD3 is an oscilloscope. Okay, so I'm going to run the oscilloscope. Now I can do this the hard way. Let's see, let's do it the hard way. Hard way first. Okay, device manager. Okay, I open up the device manager and I complain to Windows. I'm sorry, I'm not good. I'm a regular guy. I'll be careful. Right in here I can see that my particular launch pad on my particular surface is COM port 17. This wire right here, this USB cable is passing data in COM port 17. Okay? It is. 10,000 times a second, it's going to give me the value on PE3. Okay? That's how this thing works. 10,000 is not a very big number. The ones in lab are like 1 billion times per second. Billion being much bigger than 10,000. Okay. But $10,000 is a lot more expensive than free, so just do the math on that. Okay, so over here, I'm going to open up COM port 17, or I'm just going to say, hey, I don't know, just give me whatever you got. Yeah, hey, I found 17. All right, so I'm open. Okay. Now, okay, so, all right, so an oscilloscope, and this is a free oscilloscope, so don't shoot the messenger. Measures voltage on the y-axis and time on the x-axis. Okay, and I've connected it up to PE. I've connected PD7 to PF3, and that's why you can see it changing. And what I want to do is, I have one knob, just one knob, and that is to run slower. That was an F7, function F7. No, F6, sorry, that one. All right. Okay, so I only got one knob. I can adjust the time scale. Okay, the black line is actually called a trigger, but I can see that the high pulse time is not 50 milliseconds. Okay, somebody lied to you. It's 75. One of those two instructions took more cycles than they thought. Okay. So the first thing I want to do, it is oscillating at about 7 hertz or 75 milliseconds. What I want to do is change the code to sample at 2 hertz. So where in the program did it specify the delay? Yeah, right there, line 76 was where it said, hey, let's make stuff pretty. And so do I want it to go faster or slower? So I want, okay, it's 75, and I want it to be 200, right? What's 250? What's 250 low, 250 high, right? So that's 2 hertz. I want it to be 250, and so I want it bigger. I want it slower. Okay. Right? So somebody could get out their calculator. I believe that's like 60. I think that'll make it bigger by the ratio of 25 to 70. Yeah, what number is that actually? Times 1,000,000. Don't times it. It's going to get bigger, right? 3,300,000. That's fine. That's close enough. 1, 2. 1, 2, 3. Now, I could have left the code the way it was. but I need to know what that number is so I can do some more examples. Okay, so okay, whatever. They're too hard for my math. Download. Go back to my debugger. Hit the go button, and now I can see. Okay, now I gotta go slower again. Sorry. Function F5, F6, F6. Yeah, F5 crashes it. Okay. No, it just quits it. All right. So 2 hertz. All right. Okay. Okay. Now, it's full disclosure. I mean, this is. You got other classes, right? Okay, you do. 248 is the same number as 250, okay? 240, 250-ish, okay? Don't, pass your other class. Close enough. 245. 245 is still 250. As long as you know what you're doing, I don't care what number it is, all right? 240 is close enough.
Stretch it. How far can you go?
200 is close enough. I don't actually care. I mean, but 75 is not, okay? I don't, whatever, as long as you understand what you're doing, okay? Okay, so let's what if, okay? Let's go back to the program here, and what if I reduce this? So this is going at 2 hertz, right?
Yes.
All right, so I'm going to leave a comment there and leave myself a way to get back, okay, because I mess it up terribly. What if I take off 2 zeros?
Speed. Would we even able to see the flashing? Is this the 12 hertz?
Okay, this is not 12 hertz. How many hertz is it? Yeah, 200. Right? Who's with me? Yeah, and you just can't see it. So what is it you expect to have happen?
Green light. No friction.
All right, so build, download, run.
Yeah, how about 12 hertz?
Yeah, no, actually, it's not bright enough to kill anybody. So, okay, so let me just make sure. Let me just make sure it's running. Oh yeah, it's running. It's running. It's a green light. It is flashing. How would you know? Let's look at this oscilloscope. It's just flashing really fast. Okay, let's slow it down here. All right, so it is flashing at 200 hertz. Okay. I know, 200 hertz.
Wasn't close enough.
Close enough. All right, so question on what had just happened? Okay, so now we want to type away and make the code better. Okay, so it's not very friendly. So the first thing I'm going to do is I'm going to make this guy a function. Okay. And I'm going to pass in a parameter to it. And according to ARM Architecture Procedure Call Standard, how do you pass R0? So this has got to be R0. And I got to take it out of the loop here. Put it down there. And I got to end it with BXLR. Okay? All right? And then here, instead of doing the wait, I'm going to branch to it. All right? So it's a little bit more fun here. I get rid of that. All right. I didn't do much yet. Okay. Next, what I want to do is copy paste this twice. And I'm going to move. Okay. Now I guess I can OR. And then this guy was going to set high, right? And then down here, how do I clear a bit? What instruction clears bits? No, bit clear. Okay. Yeah, okay, so, right. Okay, so, okay, so now what's going to happen? Same stuff, right? Are you with me? All right, it's high, low, high, low, high, low. Okay, we're good. So that will be the same thing. Build, load. Mistake. Okay, what did I do wrong? Branch link, wait. No. Could not find the file. Okay, so wait, not defined. Okay. Oh, yeah, wait. No, wait. Okay, build. load.
Motors use magnets, so if you have a fan or a
Dilute.
speaker in there, it
All right, same thing. Now what I want to do is make the numbers different, okay? What if I make, and the way this is going to work is we're going to always make them equal to the same value. So for instance, if I subtract 22 from there, I'll add 22 from there, okay? So what do you imagine the total period of this waveform is? And it used to be 33,000, 33,000. Now it's 11,000, 55,000. How many total weights per loop? 66 still, right? That plus this is still 66,000. So the period is still going to be 200 hertz. Because it was 200 when it was 3333, and now it's 1155, right? Still, okay, build, hit the reset button, look at the thing.
Does this make it brighter or dimmer? I forgot. It's going to be dimmer.
Okay, or you made a mistake. What did I do wrong here? Yeah, question.
I think you changed it to R0.
Oh, yeah. I got a bug. I got bugs. I got more bugs. Yeah, thank you. I changed it to R0, so this needs to be R0. And then I used R0 for that, so those got to be R2s. Thank you. Yeah, these are going to be R2s. There we go. Yeah, no, better. Thank you. Points. Yeah, no, it's good. Yeah. It's, okay, the break point is there. Okay, so go ahead.
You know why? Because this is thinner.
Yeah, there we go.
This is easier to move.
Now, is it dimmer? Yeah, it's dimmer.
Or
Okay.
less dimmer. Even though it's not.
It's still going at 200 hertz. I have a small amount and I have a large amount. Okay, so next thing I want to do is abstract it some more. Okay. Question. Okay, I'm listening. Question.
So I guess, what does the equal sign do when it's in front of a number?
Okay, the equal sign does the same thing regardless of what's in front of it. Okay. The equal sign makes it a PC relative opcode, puts the thing on the other side in ROM, and a PC relative offset to it. The only difference is in assembly language, when you give a label, what is its value? The address. In this particular case, that is simply an EQU. Right? So this is nothing more than a different number. It's just that's ugly code, right? That's ugly code. Nobody knows what that means, so we'll leave it like that. Is that better?
Yes.
Okay, so basically the addresses are put there. In either case, it's a big number stored in ROM using PC relative addressing to fetch it, such that the value after the equal sign goes in the register. In this case, the value is the address. The value of the symbol.
But it's also in ROM.
It's also, there's a copy of it in ROM. So, can I, let me just, you can see them if you want. Debug, load, debug. Okay, get rid of this because I can't. I got to get rid of this because I'm on the board and that doesn't work. Get rid of that. If I click on it here, okay, let's step over. All right, there's one. Right over here, it's right over there. It tells me where in ROM it put it, and down in ROM you'll see its value.
What about immediate?
You can't use an immediate with a load instruction. The load instruction only works with register. The move can be with immediate, but it only takes little numbers.
We're doing the loader move on the bottom with the.
Okay, hold on. Where? I didn't use any moves.
With that R0.
No, that's not a move. That's a load. It's a big number. That don't fit in it won't fit in a move. Try it. It won't compile. Can I? Yeah. Let me go. Let me. I got to get there. Let me go further here. All right. So what I'm going to do, how do you make variables in assembly? No. How do you make variables? No.
You have to allocate where you're putting it.
Yeah, I know. How do I make a variable? Where do I put variables?
Registers.
No, variables. Global variables. Yeah.
Global variable.
Yeah, fine. Thank you. RAM. All right, so I'm going to make a global variable here. Two global variables.
Neela said global variables are bad.
They are. Except when you have interrupts and you're passing data from one to the other. So for example, if this PWM I'm about ready to create, okay, this variable duty cycle is occurring in an interrupt, and I want to set the duty cycle in my other thread, I have to pass that information through globals. So because we're going to have a lot of interrupts in this class, we're going to need globals for things, okay? And if you think about it, H and L in this context are permanent, and they're going to be shared. And so I'm making them global. But he's totally right. I'm just calling it now. Because they're unsecure. If you don't trust, and again, do you trust your lab partner?
No, not really.
Okay, well then don't use any, then don't,
And then his program honestly like
yeah. Okay, so I made a global and I'm initializing it. You with me?
I knew he
And notice I'm going to do it a little bit different. Oops, let's put it in 2.
actually saved out.
Okay. So what I did is I took what I found in H and I subtracted it. So this guy here is 66,000 minus H. Okay? That will cause L plus H to always equal 66,000. Okay, so what I got is H plus L is always 66,000. All right? So now I've got variables, I got to use them. I go down here and I will use them. Right here, rather than that, I will LDR R0 equals H. L, that one's L actually. LDR bracket R bracket. Okay? And up here equals all right. Okay. So what I did is I abstracted H and L. So you set the pin high, I'm going to weight H. Set the pin low, I'm going to weight L. Okay? With me? All right. And again, this will be just like the other, assuming, before I go further, let me go ahead and test it. I made a couple of typos when I did the other class. Yeah, okay, still. No, 66 hertz. No, Mr. Bill. All right, so I made a mistake somewhere. That should have been 20. I made a mistake somewhere. Let's fix it. Subtract R1. I don't know.
Yeah.
have to use moves to get the values.
No, I don't. No. They're big values. I got to use LDR. LDR. No, I don't know. Let's just put a breakpoint here and see what happens. Okay. Debug.
I think I'm like not at that point. I'm like, here's like that level of degeneracy needed to understand. I'm like, here, it's like not there yet.
Step over. I don't know. All right, let's H and L. I somehow messed it up. 66,000? Two, 66 minus that. It don't matter. All right, let's. Can I borrow the the solution here? I want for you to describe. No, not that one. This one. No, not that one. This one. That was the right one. Yeah, there we go.
Oh, sleeping.
Describe the behavior of this light.
No, it's breathing.
Off and then turn it back on.
Oh, sounds scary. Dying.
It's going on and off.
My school life.
Yeah. So how in my program, how would I make the brightness of the brightness of this LED? How would I make it change? Change the duty cycle. But if I told you this were sinusoidal, okay, here an easy one would be a ramp. What if down here I took H? What if I took H here and added 1 to it? So if I just loaded it, okay, and let's add 1,000 because I can't wait that long.
Oh, you're just increasing the.
It's gonna increase.
You're increasing the hertz.
I'm not increasing the hertz because aside from my bug, which I don't know what it is, I changed H. I got to store it back. Don't forget to store it. Oh yeah, now add it to R1, not to R0. Okay, if I add 1,000, H is going to go up, but L is going to go down. Okay, so what am I going to see in terms of brightness as a function of time? I'm going to see an increase. So if I wanted to plot what that looks like, it would be 11,000. Right, and then this would be 11,000 plus 1. Oops, missed it. See, plus 1,000 equals this plus 1,000. All right, fine. You're dishing the. All right. Right, and so if I were to plot this, what is it going to look like? Until it crashes. Right? Because it can't go over 66,000. Okay? What if I wanted something other than, if it got up to, 65,000, I could set it back to 1,000. Okay, that's the easy way. But what if I wanted to make it sinusoidal? No. Okay, think about it. I want a sinusoidal power. I want to see power as a function of time, sinusoidal. Yeah, I'm going to stick it in the AC. No, it turns out that wouldn't work either. That would just blow it up. I don't polynomial. I don't. If you asked him if you would like to have a quadratic, have a quadratic. But if you wanted to have a,
Fourier's not gonna help you here, okay?
before I get there, you're going to have to tell me what frequency you want it oscillating at. And so I'm going to guess 1 hertz. So I'm going to need 200 points.
12.
All right. So the first axis is going to be the index to something that we love endear, both 312 and 319. And the second is going to be an amplitude. Okay? And I just got to get my math right. I got 33,000 plus, I'll do it easy in here, 20,000, 30,000 times, I'm just going to use a cosine or sine of this times 2 times pi. Okay, divided by, I'm going to have 200 elements in my array, not 2,000. All right? The trouble is that's some weird number. Okay, fix my problem. Whatever. Oh, yeah, I need a times in there. Okay. Yeah, right there. I need a times. Okay. And so what I'm going to do is I'm going to round this to an integer. Spell it right. So this is going to be my h, by the way. So my h, now if I were to plot this one's interesting. I'll plot this one. Insert, plot. Pretty lines. Come on. That'll work. Okay? That is good. So if h is 62,000, what is it going to be? Bright. If h is 1,000, what's it going to be? Dim. And it's going to go back and forth. Okay? So how do I get all of these fun numbers into my software? You got a lab partner. Hey, lab partner, it's only 200 numbers. Copy them over. Fine, whatever. You can do it in MATLAB, but you still got to copy it over. You still got to. So I'm pasting them as characters. Where's my characters? Oh, I don't want the plot. I don't want the plot. And I want the plot. Give me the thing right there. I want these numbers here. I'm going to take these 200 numbers here, paste them into here. There we go. Change the carriage returns to comma space. All right, so now let's get back to 319. What is it? What is it that's in my clipboard? What is that? It's an array. Yeah, sure. What kind of array is it? I know. Is it global, local, ROM, RAM, stack, registers? Where are you going to put it? You can't make it local. We don't have enough stack space.
Heap.
Okay, you could put on heap. You could, but it's going to be. Look at my thing. Do I ever need to deallocate it? Oh no, it's over that one.
Just follow the same pattern when you get to the end. Repeat.
I know, but where am I going to put it? Not in RAM, because I shut the power off. It's going to go away. I got to put it in ROM. Okay. I got to put it in ROM. So how do you put crap in ROM?
Code space. Area code.
Right here. I'm going to put it there. Okay. And so I need a name for such a beautiful thing.
The sky.
Hey, yeah. Life.
That sounds like good
Life.
poetry.
Oops, not there.
Life.
All right. And now I need a pseudo-up, which will store. These are 16-bit numbers, 32-bit numbers. They could have been 16, but they're 32-bit numbers. So I need a way to store a bunch of 32-bit guys, and I'm going to use a DCD. Okay, so I just allocated an array of 200. So rather than doing here, let me just write pseudocode, because I'm almost out of time. Let me add pseudocode. Rather than this pseudocode, okay, what if I had what if I said H were to be equal to life bracket I, and L were to be equal to 66,000 minus H, okay? And what if I were to do I equals I plus 1, okay? And if I equals 200, set I back to 0, okay? How fast would this thing go through the loop? How long did it take to go through how long did this take? Exactly how long did it take to do that? Not 200. How much time? How much time does it take to execute that highlighted code? 5 milliseconds. 1 over 200. Okay? And if I go through each entry of the table, each time through the loop, how long did it take me to go through the loop?
A very small.
No. Exactly what? How big was my table? 200. Exactly 1 second.
I would hesitate to say exactly.
Well, as exact as the 5 is millisecond, right? The 200 is exact. The 5 was approximate. Okay. All right. 319 issue. What is the addressing? How do you address into an array of 32-bit numbers? Base address plus what? Yeah, but what I? I is your index.
4 times index.
4 times the index. Okay? All right. So what I got to teach you now is the conditional. So questions on that? Yeah, look at this one. This other one is not a sinusoidal. It's got loosey wires. It's called Perlin. P-E-R. P-E-R-L-I-N. Perlin. And it's something that psychologists have said people think is alive. It's obviously completely made up. But the problem, the beauty of this is I can put any shape in here, right? I just map the shape in terms of my table. All right, let's go back to some TK stuff. Okay. All right, so this is a review for what we said. It's called pulse width modulation, which is a way to adjust the power. This is ubiquitous. It's in your electric cars. It's in your diesel locomotives. It's in your aircraft carriers. Anytime you have, it's in the dimmer for the lights. Anytime we want to control power to a device, this is a very flexible way, because in my code, how many different settings did I have? Think about it. How many different settings? How many different things could H be? No, exactly how many? No.
66,000.
66,000. I had a knob of 66,000 settings that I could set for the brightness of this LED. That's a lot. That's 16 bits of precision. Okay. what is the relationship between H and power? It's linear. Because V and I are constant, because H plus L is constant, this is linear. All right, let me, we got 4 condition code bits. N means negative, 0 means, Z means 0. The way this works in assembly language, when I want to do an if-then statement, you use 2 instructions. A compare instruction with 2 parameters in it, followed by one of these 6 conditional branches, assuming R0 and R1 were unsigned. Okay? And so branch low will branch to the target if R0 is less than R1 unsigned, greater than equal to. If they happen to be signed, we're going to use a different 6. Well, equal and not equal are the same, but the other 6 are different. Whose job is it? Whose job is it to know whether the number is signed or unsigned? You. We've seen a couple of ways in which it mattered, right? LDR SH versus LDR H. We're seeing another way in which it matters, and that is after a comparison. If it's unsigned, I'm going to use these unsigned branches. If they're signed, I'm going to use those signed branches. Okay? So if I want to know whether it's equal to 0 or not, then that's not too complicated. But again, if I'm trying to compare the index I to the number 200, you have to know whether 200 and I are signed or unsigned. For you to tell, well, they're probably unsigned, for you to do a conditional unsigned branch. And so the flow chart for an if-then statement, obviously, is I'm going to compare. I got 2 possibilities coming out of this. This is the true possibility, and that's the false possibility. So it will go to the instruction after the branch if the branch condition is false. Just like everything else we've done, write some C code, click on it, and you can see what it did. Okay, it's going to use a compare followed by conditional branch. Any questions? Lab 3 is getting to be a little more fun than Lab 2 because the light will at least flash. Lab 3 will have a partner. Go ahead and look at Canvas. I made a bug. There's a bug in the simulator when we get to Lab 3. I won't fix it. I just have a workaround. Yeah, so read the Canvas note about my bug in Lab 3. Yeah.
Can you just go back one slide?
These are all posted.
Yeah.
It's fine. That is fine. That one. Yeah. All right. Well, have a good weekend, and we'll see you on Tuesday.
Talking about mono, can you
Yeah.
explain
Let me shut off the recording.